Hello, everyone. Welcome to today's session. I hope everyone's doing well and staying warm with the snowstorm. If you have access to the worksheet, go ahead and pull it up. And today we're going to be looking at viruses, and it's relatively a short worksheet compared to the ones we've been doing before. So we might end early today. Okay, I hope everyone can see my screen and hear my voice. If not, please let me know. All right, let's get started with the question. We're just going to go down the worksheet. So the first question says, by definition, viruses are obligate intercellular parasites. What does this mean? So can anyone tell me what obligate intercellular parasites are and why viruses are considered that? So when you think about a virus, they're usually non-living when they're outside of a host, but when they're inside of a host, they can use their genetic material and like use their protein mechanisms and stuff. So that kind of relates to why viruses are called obligate intercellular parasite. And that means, yeah, in the comment it says use host cell machinery. Yes, that's right. So viruses without the use of the components in the host cells, the viruses can't replicate their stuff. So therefore, they need a host to reproduce and to survive long term. So by definition, obligate intercellular parasites are ones that can neither survive long term nor reproduce outside of a host. One of the comments says, sorry, I'm a little late. What was the form for attendance again? So I think what I'm gonna start doing from now on is put the link at the end of the chat, because if I put it in the beginning, if people come in the middle or later during the session, they're not able to see it. So what I'm thinking is at the end of the session, I will put the link in the chat. Okay, and then the next question we're going to be looking at how viruses are classified. So generally, viruses are classified on the type of genetic material that they have, so the nucleic acid that they contain. And we know that viruses can be either single-stranded or double-stranded, RNA or DNA. So based on if it's RNA or DNA, and whether it's single or double is how we're going to be classifying different types of viruses. All right, next, can anyone tell me what reverse transcriptase is and why it's particularly useful for viruses? All right, I'm seeing some great comments here. One of them says reverse transcriptase allows RNA to be transcribed to DNA. The next one says it is able to make viral DNA so it can affect the host. So yeah, so the reverse transcriptase is useful to allow, is especially useful for viruses that contain RNA, and we need it to be DNA. And like the second comment says, that's how it can affect the host. So we need the RNA to be converted to DNA, and the reverse transcriptase is very helpful for that. And can anyone tell me what kind of viruses reverse transcriptase are found in? So what kind of virus contains RNA as opposed to DNA? Yes, retrovirus. Good job. So these are particularly useful in retrovirus, and they were actually discovered in retroviruses. Oh, and also it's an enzyme, so that's important to note that reverse transcriptase is an enzyme, and like most enzymes, it ends in ase. So even if you didn't know it's an enzyme, that would be a good guess based on how the name ends. Also, the reverse transcriptase is very useful for scientists today because you can use it to make genetic recombinants, and that helps us make cDNA from the mRNA. And so, if we're trying to insert genetic material from a like eukaryote to a prokaryote, it avoids the problem of eukaryotic introns. So it's really helpful to use reverse transcriptase in genetic recombination. All right, so the next question we're going to be looking at how viruses invade other cells and why it invades other cells to reproduce. So we'll be looking at the general process of viral reproduction, including the two types of viral cell cycle. So there's the lysolytic viral cycle and the lysogenic viral cycle. Can anyone tell me the big differences between those two cycles? comment says virus invades cells to use ribosome to copy their data. Another comment says one affects the host and one just lives inside and does nothing. Getting more comments. Isn't one held from further replication? Lysogenic is cutting into two, correct. Yeah, so I feel like all the answers are touching upon like the general idea. The last comment says Lytic cycle kills the host cell. Yeah, that is a great response, and that's one of the main differences. So generally, viruses can fall into two categories. They're either the lytic cycle or the lysogenic cycle, and also some like go back and forth between both cycle, like how there's alternations of generation. So viruses have this like alternation of life cycle as well, where they go between lytic and lysogenic. So the main difference is that in the lytic one, it actually lyses the cell. So the virus like multiplies, and then in order to release the new viruses, it like breaks the cell open and like puts them all out to like go invade more cells. Whereas the lysogenic, what it does is that it incorporates like its own DNA into the host DNA, and it remains there for a while, silent. Like it isn't doing anything, but it uses the host material to keep regenerating, to keep multiplying, and then later it comes out of the host's DNA and enters the lytic cycle. And then when the environment's right, it's gonna disperse its viruses again. So one is very quick. It's like entering the cell and then it rapidly multiplies and then just breaks out of the cell and it kills the cell in the process, kills the host cell in the process. Whereas the other one inserts its own DNA into the host DNA and stays there for a while. And one of the advantageous of this is that if you kill the cell, then you're not going to have cells left to replicate in. So one advantage of the lysogenic cycle is that it uses the host cell for as long as it can and continues developing in it. And when the environment's right, then it's like, okay, now it's like time to break out of here. Did that make sense? Any questions on that? Yeah, another comment. Sorry, I'm just seeing this. It says lysogenic includes the viral DNA to the host DNA and lays dormant for some time. Yeah, yes, that is exactly right. So I'm just gonna write down what I said in a concise form, so if, when you're referring back to it, it'll be easy to read. Also, a way that I like that helps me remember the difference between this is that lysogenic has genic in it, and that kind of looks similar, like genetic to me. So I know lysogenic is the one where it inserts its gene into the virus, and then lytic, I guess it's just the other one. That's how I remember it. But you can also remember that lytic is shorter than lysogenic, so you can think about it as like it's like chopping up the cell and like destroying the cell. But yeah, I like to think of this as genetic, and that helps me remember that this is the one that inserts the gene, and the other one is the one that breaks the cell open. Okay, so the next part, can anyone tell me what type of viruses are more likely to have the lysogenic phase? So viruses that have double-stranded DNA and retroviruses are the ones that are able to, bacteriophages, yes, that's a good example because I think they are a retrovirus, right? Animal ones. Yeah, I feel like generally animal ones are retroviruses or double-stranded DNA. But the the broader category is that most viruses with double-stranded DNA or retroviruses that can produce double-stranded DNA tend to do the lysogenic phase because then they can incorporate their double-stranded DNA into the host double-stranded DNA because the eukaryotic cell is going to have double-stranded DNA, right? So that's why RNA viruses that do not produce DNA as the template can like are not able to incorporate their DNA just because it's so different from the double-stranded DNA. And then just remember that RNA viruses that can't be converted to DNA won't be able to do this lysogenic phase. Okay, so the next question says more than 100 different viruses, many of them rhinoviruses, can cause the common cold in humans. Other viruses, influenza viruses, cause the flu. Although there are many different antibiotics for treating bacterial infections, relatively few drugs are available to treat viral infections. So, can anyone tell me why it's a lot harder to treat a viral infection than a bacterial infection? think about what what antibiotics do to the bacterial cell versus what viruses have or don't have. Comment says viruses use our machinery. Yes, that is the right answer. So bacteria, unlike humans, have their unique things. So they have their 70s ribosomes, they have their bacterial cell wall, they have bacteria-specific enzymes. So that is very different from the stuff that's in our body. So therefore, when we put antibiotics, it knows exactly what to go and attack. But on the other hand, viruses just have protein and then they have their genetic material, which is very similar to what we have. So therefore, it's a lot harder for the drugs to be targeted. So it can like potentially like destroy our own cells as well. Oh, and another thing about viruses that makes it hard is that they they reproduce faster. So there's like a high rate of mutation, and it can make it like very difficult to develop drugs or vaccines against it. Like a great example of that is reverse transcriptase has like an error rate of 1 to 8,000, whereas like other DNA polymerases typically have like 1 in a million. So like the fact that their reverse transcriptase makes a lot of mistakes also leads to like random mutations. And I feel like this is also like super relevant today with like how on the news we're seeing like all the different like strains of coronaviruses coming and like people being worried about like the efficacy of vaccine or like scientists testing like how efficient it's going to be with the new strain of the virus. Oh, also I saw the comment about the attendance link and I will be linking that at the end of the stream. Okay, so the last part we're going to be looking at today is developing a drug combination to effectively combat multiple infections. And there's going to be like multiple ways to answer this, but we're just going to look at like a couple of answers that could work here. So it says that Patients with AIDS often acquire opportunistic infections. Imagine a patient with AIDS and two opportunistic infection, a respiratory disease caused by Mycobacterium and another caused by the fungus Candida. As the patient's physician, you need to prescribe drugs to counteract the infections. Given the normal anatomical and functional characteristics of each disease organism, what characteristics should a drug combination have to treat each of these three infections while doing the least harm to the patient? So this is kind of similar to the last question we answered, where a drug is most effective and least harmful when it can specifically target that pathogen and not harming the host. So for a bacterial infection, we would want to choose a medication that is specific to that bacteria, like it attacks something that only the bacteria has and does not attack the components of the host's body, in this case, the human. So we're going to be looking at the three diseases that this person has and what kind of drugs we can use to just combat that specific one. Okay, so I'm just gonna at the top write down the three. So it was AIDS, Mycobacterium, and Candida. So we're gonna look at treatment that will address each of the three infections separately. And we're gonna try to find things that are unique so we can only attack that. So for AIDS, the patient probably will need continual treatment, and that's because, or they'll need continual treatment with like several types of drugs because the virus is eventually gonna like adapt and like resist most treatment, so they're gonna need to be continually treated with different types of medications. And for specifically targeting, we could look at treatments that could inhibit like proteins on the viruses, because like they have the capsid, right? So maybe something that can specifically target that protein that like humans don't have. Um, or we can target proteins that help the virus like enter or leave the cell because that's how they're like reproducing really fast, right? Like they're entering a cell, they're replicating and either breaking or inserting their DNA. So if we can find a drug that inhibits like going in and out of the cell, that could definitely help like stop or slow it down. Um, Another way we could do it is if we find drugs that inhibit reverse transcriptase. So say that this is a retrovirus and that it needs to convert RNA into DNA. In that instance, we can find a drug that inhibits the reverse transcriptase, and in AIDS, it is a retrovirus, so a reverse transcriptase inhibitor drug would be very helpful. But the treatment for AIDS is like in real life, like very difficult, just because it has DNA and it can like integrate that into human chromosomes and lay dormant for a very, very long time. And this disease, AIDS, is known to go through rapid evolution. So it like even if doctors are like treating patients, it's like constantly changing. So it makes it like very hard to treat this disease. Um, but yeah, like existing drugs like try to destroy the virus mutants, and like try to prevent the continual infection, but it's like very hard to treat in real life. Okay, so the second one is the mycobacterium. So because this one is a bacteria, we can safely look at antibiotics option. And like in the earlier questions when we discussed how bacteria have like different traits than humans, or like different proteins and things like that, it's going to be relatively more easier to treat this than AIDS. So what we can do is find bacterial, like antibiotics that are going to affect bacterial protein synthesis, because if we prevent bacterial protein synthesis, then they're not going to like have the same effect that they would. So they will still be able to like go through transcription translation, but they will not be able to produce the outcome that they intend. So if we like, there's drugs that affect their 70S ribosomes. And this is very helpful because humans don't have 70S ribosomes. We have 80S ribosomes. So if we use drugs that affect 70S ribosomes, it will effectively kill the bacteria while not destroying any of the components of the human cell. Oops, I meant to say since it's a bacteria. Okay, and the last one is the Candida. So this one is a yeast, for people that are curious. So I guess I can write that out too. So virus, bacteria, and the last one is yeast. So another problem with yeast is that they are eukaryotic cells, So they're going to be very similar to eukaryotic cells in their structure and function. So it's going to be a little bit harder to treat than the bacterial infection as well. But but we can target their fungal cell walls because humans don't have cell walls in their cell, but yeast do. So that's one difference that we see. So typically, drugs that are targeting yeast are going to be targeting their cell wall. Another thing we can do is destroy the fungus exoenzymes, and those are needed to break down proteins usually, or sorry, break down nutrients. So if we destroy that, then they're not going to have any way to get nutrients and grow more. So two types of drugs that would be useful for yeast would be drugs that target cell wall, or drugs that break down the exoenzymes. Okay, that brings us to the end of our lesson, and we finished a little bit early compared to our other sessions. I would say, like, the big takeaway from this worksheet is knowing why viruses are obligate intercellular parasites, and that leads us to like how viruses are classified. So I would start off with that, like what are the different groups of viruses, like the big picture, RNA virus or DNA virus, double-stranded or single-stranded. And then I would know that retroviruses need reverse transcriptase to get from RNA to DNA. And I would also know the two different cell cycles, so the lytic and the lysogenic. And then I would also know that RNA viruses that cannot be converted to DNA cannot go through the lysogenic cycle because they won't be able to incorporate a single-stranded DNA, or sorry, single-stranded nucleic acid into a double-stranded nucleic acid. And then from the last part, it might not be very necessary to know like the specific details of like a mycobacteria or a candida, but I would know like the general difference between virus, bacteria, and yeast and how they differ from a human cell. So if they did ask a question about like, oh, what kind of like drug would be most effective on a yeast, like you would know that they share a lot of things with eukaryotes, so it would either be like cell wall or their enzymes. So those are like the big pictures from this worksheet, and let me know if you have any questions. And comments saying, is this document available? Yep, it's on D2L. Yeah, okay, thank you for answering that. All right, okay, here's the extra credit form, so make sure to fill it out to get extra credit, and let me know if you have any questions. Thank you everyone for coming today. I know it's been like a rough week with all the like midterm canceling or like changing dates and like bad internet connections and like no power too. So So glad you guys are still excited to learn. All right, I'm gonna stop the streaming, but again, like make sure to fill out the worksheet or the Google form so you can get extra credit and have a great day, everyone. Thank you.